Paraconsistent logic is a family of non-classical logical systems designed to handle inconsistency in a controlled way. In classical logic, a contradiction, a statement of the form A and not A, leads to triviality. From a contradiction, and also from an inconsistent set of premises, any statement whatsoever can be derived. This principle is often called explosion. Paraconsistent logics reject this principle. They allow contradictions to exist in a theory without collapsing the system into triviality. In such logics, it is possible for a theory to contain both A and not A without entailing every possible conclusion. Thus, the defining feature of paraconsistent logic is that inconsistency does not imply triviality. There are several motivations for developing paraconsistent logic. One important motivation is the idea that there may be inconsistent but non-trivial theories. In real-world reasoning, we often encounter bodies of information that contain contradictions but are still useful. Classical logic cannot handle such situations without collapsing into triviality. Another more controversial motivation is the claim that there may be true contradictions. According to this perspective, certain paradoxes, such as semantic paradoxes involving truth, may involve genuine contradictions that are nonetheless true. Further motivations come from linguistics and philosophy of language, where natural language sometimes appears to tolerate inconsistency without breakdown. Paraconsistent logic has also been proposed as a tool for dealing with semantic and set-theoretic paradoxes, such as the liar paradox or Russell's paradox, without rejecting large portions of classical reasoning. In more practical contexts, paraconsistent logic is useful, or so it has been argued, for belief revision, where agents must reason with temporarily inconsistent information, and for modeling legal or normative systems which may contain conflicting rules. Finally, paraconsistent logics have applications in artificial intelligence and automated reasoning, where systems must operate reliably even when their information sources are inconsistent. The key idea behind paraconsistent logic is to block the inference from a contradiction to arbitrary conclusions. This typically involves rejecting or modifying certain classical inference rules, especially those that allow unrestricted use of contradictions. As a result, paraconsistent systems often preserve much of classical reasoning while carefully restricting the principles that lead to explosion. The challenge is to balance expressive power with controlled reasoning in the presence of inconsistency. There are several different kinds of paraconsistent logics, each implementing the basic idea in a different way. Discursive logic interprets contradictions as arising from different points of view or contexts. A contradiction may be tolerated because its components hold in different perspectives. Non-adjunctive systems reject or restrict the rule of adjunction, which allows one to infer A and B from A and B. By limiting the rule of adjunction, these systems prevent contradictions from spreading uncontrollably. Preservationism is an approach that tries to define a new consequence relation. It treats logical inference not as the preservation of truth, but as the preservation of consistent fragments, or the degree of coherence within a set of data. Preservationism is a form of non-adjunctive logic. Adaptive logics dynamically adjust their reasoning. They proceed as if the information is consistent but revise conclusions when inconsistencies are detected. Logics of formal inconsistency explicitly represent consistency within the language. They include special operators expressing that a formula is consistent, allowing the system to distinguish between harmless and problematic contradictions. Many valued logics introduce more than two truth values. For example, a statement may be both true and false or neither, which allows contradictions to be represented without triviality. Relevant or relevance logics restrict inference to cases where premises are relevant to conclusions. Many relevant logics are also paraconsistent because they block explosion by requiring a meaningful connection between premises and conclusions. Each of these approaches reflects a different philosophical and technical strategy for dealing with inconsistency. The syntax of paraconsistent logics is often similar to that of classical propositional logic, with connectives such as negation, conjunction, disjunction, and implication. The differences lie primarily in the inference rules and semantic interpretations. Semantically, paraconsistent logics may be interpreted using, for example, many-valued truth tables, where formulas can take more than two truth values. Relational or possible world semantics, sometimes with non-standard accessibility relations. Algebraic structures, such as non-classical lattices. These semantics are designed to ensure that contradictions do not lead to triviality. In paraconsistent logic, logical consequence is defined in a way that preserves non-triviality. A conclusion follows from a set of premises if it holds in all models of the system where the premises hold, but contradictions in the premises do not automatically make every conclusion valid. Validity is therefore weaker than in classical logic. Some arguments that are classically valid fail in paraconsistent systems because classical systems rely on explosion. Propositional paraconsistent logics can be extended in various ways. They can be combined with predicate logic, allowing quantification over individuals, or with modal logic, enabling reasoning about necessity, knowledge, or obligation in inconsistent settings. Paraconsistent logics are also used in areas such as database theory, legal reasoning, and artificial intelligence, where inconsistent information must be managed rather than eliminated. Paraconsistent logic challenges a fundamental assumption of classical reasoning that contradictions entail anything. By allowing inconsistency without triviality, it provides a framework for reasoning in complex and imperfect informational environments. Whether motivated by philosophical considerations, paradoxes, or practical applications, paraconsistent logic has become an active and growing area of contemporary logic.